Building computational self-models of robot bodies, or the ability of a robot to simulate its physical self, is an essential requirement for robot motion planning and control. Similar to humans and animals, robots can use self-models to anticipate future outcomes of various motion plans without explicitly trying them out in the physical world. Recent progress in fully data-driven self-modeling has enabled machines to learn their own forward kinematics directly from interaction data. However, existing methods can only predict limited aspects of the robot morphology, such as the position and velocity of the any effector. The pre-assumed predicted scope limits the general applicability of these self-models to future, yet unknown 3D spatial planning tasks. For example, a self-model focusing only on predicting the position of an end effector may not be useful for tasks involving operation in a crowded workspace, where full-body collisions must be factored into the planning. In this paper, we present a full-body visual self-model that captures the entire robot morphology and kinematics using a single implicit neural representation. Our visual self-model is able to answer space occupancy queries given the current state or the possible future states of the robot. For example, it can answer a query as to whether spatial position XYZ will be occupied if the joints move to some specified angles. The response from the neural network to a series of queries can then be used for a variety of tasks such as motion planning, collision avoidance, damage assessment, or the visualization of the entire robot, to name a few. All these aspects will be demonstrated in this video. This ability to sense post-conditioned space occupancy is similar to our natural human ability to see in our mind's eye whether our body could fit through a narrow passage without actually trying it out. We demonstrate our approach on a robot arm with 4 degrees of freedom. Initially, the robot moved randomly and it collected pairs of joint angle commands and a fused multi-view point cloud. After several hours of learning, here you can see the acquired self-model became more and more accurate to match the real robot pose. Here, we show more side-by-side examples of our predictions on unseen inputs of the joint angles. By learning directly from high-quality simulated data or real-world noisy data, our visual self-model can learn accurate full-body morphology and kinematics. Here, we show more predictions by interpolating between input joint angles. Our visual self-model is a single network with implicit neural representations. The input has 2 components, a spatial coordinate and a set of joint angles. The spatial coordinate is passed through a coordinate network to get the coordinate features, and the joint angles are passed through a kinematic network to get the kinematic features. Both features are then concatenated and processed by another few layers of the network to output a zero-level SDF value. All layers of the network are simple MLPs with sign activation functions. The entire network weights require about 1 MB memory. Overall, our visual self-model supports continuous query at both spatial coordinate domain and control signal domain. Our visual self-model is also memory efficient, fully differentiable, kinematic aware, and human interpretable. Once acquired, the same self-model can be reused to solve inverse problems for multiple motion planning and control tasks without any retraining. Since our model is fully differentiable, we can freeze the weights of the visual self-model and directly perform a gradient-based optimization with respect to the input angles. Here, we experimented with 3 tasks. In the first task, the visual self-model needs to generate the goal state of the robot to touch a sphere with any part of the robot body. Here, we overlay the prediction of our visual self-model with the real-world execution of the robot. In the second task, the visual self-model needs to generate the goal state of the robot to touch a sphere with its any-effector link. Here, we overlay the prediction of our visual self-model with the real-world execution of the robot. We can easily run the optimization steps in parallel. On a single GPU, our visual self-model spent 3 seconds and 5 seconds to get the solutions for these two tasks with a precision of 2 cm. For the third task, we can combine our visual self-model with existing motion planners in a plug-and-play manner. Here, we task the self-model to generate an entire safe trajectory to touch the sphere with its any-effector link without colliding with the red obstacle. The robot spent about 7 seconds on a single GPU to generate the entire plan. Overall, our robot achieves 97% success rate on this task. Furthermore, when there are real-world damages or changes on the robot body, such as broken motors or changed topologies, our visual self-model can first detect the change, identify the specific type of the change, and then recover from the change. Here, our visual self-model identified the damage where the second motor was broken and the corresponding joint always stayed straight. With 50 new observations of its current morphology, the visual self-model updates its original internal belief to match the real-world observations on the right. Here, our visual self-model detected damage where the any-effector link was extended by a 3D printed stick. Similarly, the self-model updates its original internal belief to match the real-world observations after 8 minutes of training on 50 examples. Overall, our method opens up a new opportunity to learn a visual self-model of robots that is 3D aware, continuous, memory efficient, differentiable, and kinematics aware for fast motion planning and control, with the potential to scale to other robotic platforms and applications such as locomotion and object interaction. For more information about our paper, dataset, or codebase, please visit our project website. Thank you.